Chapter 2. Talking about atoms and elements. No, that still doesn't work. Okay. So let's think about a piece of graphite from the tip of your pencil. You know how when you press too hard, a little piece breaks off. If you took that piece that broke off and you cut it in half, and you took one half and you cut that in half, and you took one half of that and kept cutting it in half, what would happen? Now, obviously, we get to a point where whatever you were cutting it with would just kind of smash it instead of cutting it in half. But imagine you had an infinitely thin knife and you could see incredibly small things and you just kept going. What would happen? There would come a point where you would get down to two atoms and you would divide those in two, and then you're down to one atom. And you can't go any further than that. So the word atom comes from the Greek word atomos, which means indivisible. You can't divide a carbon atom into smaller pieces and still have carbon. So atoms, like I've said, I think of as the Lego blocks, the building blocks of matter. If we want to understand matter, we have to understand what these atoms, these smallest indivisible particles, are all about. So 1827, a guy named Brown looked through a microscope at some water-suspended particles that had come from pollen grains. And he saw something rather puzzling. So let's watch a video. This obviously was not taken in 1827. Come on. Zooming in. Those are the particles he saw. They almost look alive, don't they? They're wiggling. It's a very short video. So, you want to watch it again? Okay, we can do that. I know, it was so fast, some of you probably blinked and missed it. So these are the particles that he observed, and they are moving. And this is now called Brownian motion, because Brown was the first guy who observed and documented that. It's kind of catchy music. So he saw that those particles were moving. And so then, of course, you're asking, well, why? Why are the particles moving? Why do most things move? Because they're alive, right? So he initially thought that they might be alive, but then he, after further study, he concluded that the source of the motion was not coming from the particles themselves. It was something outside the particles that you could not see in the microscope that was causing them to move. So fast forward a few decades, 1905, Albert Einstein developed a theory that explained Brownian motion. So Brown discovered this phenomenon, and it was called Brownian motion, but people didn't really understand what was causing it till Einstein came along. And he developed a theory that says the Brownian motion is the result of molecular bombardments of the particles due to the thermal energy of the surrounding water. So the idea here is that the water molecules in the liquid, which are moving, much like students are moving during lab, everybody's milling about, right? That's what water molecules in the liquid are doing. As those water molecules move apart, they're continuously bumping into, pushing around those little pollen pieces and the dust particles, causing them to oscillate and move. And so this is a lot like a beach ball that's thrown into a large crowd. And people just, kind of hit it when it comes to them. And it doesn't necessarily travel around the stadium, right? Unless you've got a concerted effort going on, but who can coordinate that many people? Right? People just hit it, and so it just kind of jumps back and forth, tends to stay in sort of the same area. So those pollen grains and dust particles are like the beach ball. And the water molecules are bumping into them, causing them to move. So this inferred the existence of atoms, because if those particles are being bombarded, something has to be hitting them, right? Anybody have any questions about what Brownian motion is?
So it has to be something from the outside moving something from the thermal energy.
Yeah, the thermal energy of the water molecules. The thermal energy means that the water molecules are moving. We're okay with that? We can't see the water molecules in the microscope because they're too small. But when those water molecules hit the particles, then they cause the particle to move. So you could think of it as being a bit like maybe you had glow-in-the-dark beach balls and all the lights were off, right? And people are hitting the beach balls, but it's dark, you can't see their hands. But you see the effect of their hands as the beach balls jiggle around in the crowd. So from this, they said, this suggests that atoms are real. You can't zoom in enough on a microscope to see them, so it's a little bit tricky. So a guy named Jean Perrin, he died in 1942. He did some experimental measurements and confirmed Einstein's theory. And that was really when we were like, okay, that seals it. Nature has individual particles. While we still, question?
Just make sure we don't really need to focus as much on the history side, like the dates.
Correct.
And everything.
I am not going to even ask you who discovered Brownian motion, although it was Brown, right? That would not be too hard. So I'm not going to quiz you on any dates. And there's only a couple of really big names, like John Dalton. But most of these guys, I just want you to have heard of them. So we still cannot zoom in with an optical microscope and visualize atoms. But back in the 1980s, a couple of guys at IBM in Switzerland developed something called a scanning tunneling microscope. So the way this works is you have this probe, and at the tip of the probe is a very fine point. And at the point of this it really comes down to a single atom. They apply a voltage and measure the current between the probe and the surface. And the current that flows depends on the distance between those two things. And so by moving the probe in a way that keeps the current constant, you can move the probe at a distance that is the same as it goes over the surface. Now the surface is not completely flat. It looks flat, but it's got bumps from atoms and stuff on it. And so as it goes along, the computer controlling it will cause it to move up and down. And it's a scanning microscope because it scans back and forth. And then it takes the information and the computer generates an image. So STM allows us to image and even move individual atoms and molecules. And this picture is a scanning, tunneling micrograph of atoms. Here they've taken iron atoms and moved them around on a copper surface to write the Japanese characters, the kanji characters for atom. Obviously someone had a little bit of time on their hands. So let's watch a couple of videos about that. Let's see. Wait, that's not the one I wanted just yet. Oh yeah, it is. Never mind.
So what we do to move atoms is a variation of what we do to see the atoms in the first place. So we can't use light to see them. So we're not looking through a microscope like the conventional microscope we're used to. We need something that can see much smaller things than that. So what we do is take a sharp metal needle and bring it close to the atoms. And in a sense, we're feeling the shape of the atoms. So if you imagine that we have a surface that we're putting an atom on, we put it on a surface so it holds still. What we do is take this metal needle close to the atom and sense its presence by measuring an electric current that flows. And as the tip of this needle approaches the atom, it sees more electric current, and we draw it up and over the atom to keep that current constant. So in a sense, we're feeling the shape of this atom. Then in order to move atoms, we observe that we have a sharp metal needle near it. We can bump into it by accident. What we can do is, instead of doing it by accident, do it under control. If this is our atom on a surface, we can move the tip close and we start to form a chemical bond between the tip and the atom. That chemical bond forms between most atoms. They like to bond to each other in most cases. So we start to form a bond such that the atom follows the tip around on the surface. We can drag it to a new spot. When we withdraw the tip, it holds still because the surface is holding it in place. And we can take an image and see where we've placed this atom. So that process, repeated over and over, is how we've built most of the structures in our lab. That's our bread and butter basic technique for moving atoms around.
There's a bunch of different videos that IBM has put out here. So IBM developed this because if you can move individual atoms around, you can make electronic circuits that are smaller, right? There's a limit to how small things could be. You can make an electronic circuit where the individual wires are 1 atom thick. You really can't go any smaller than that. But in order to make something that small, you have to be able to move those little tiny, tiny particles. And so they could move them around and take images like this. Now this image seems to suggest that the atoms are cone-shaped, right? They're not cone-shaped. They're actually spheres, but the instrument only has limited resolution, and so it's like a fuzzy picture of the atoms. So you can make still pictures, and they also made a movie. And you could say this is the world's smallest movie. So there's another movie that shows more specifically how that movie was made. Isn't that fun when they make movies about making movies? But you could think of atoms as like the ultimate pixel, right? We're all familiar with electronic displays, computer screens, cell phone screens. And the resolution is the number of pixels across, right? Well, we keep making better and better ones with smaller and smaller pixels. And so we've got, resolution on our little iPhone screens that's just mind-boggling. It's much sharper images than we used to have on full-size television sets. But there's a limit to how small that can go, and that would be individual atoms, because that's the smallest particle there is. So just to kind of try to help you understand how small those pictures are. If you took all the words in the books in the Library of Congress, so the Library of Congress, there are 35 million books. If you measure the length of the shelves that they're on, 840 miles of books. Not laying flat, stacked vertically, right? So they're much closer together. 840 miles of books, all the words in all of those books. That's a lot of words. If you wrote them in the size of those kanji characters on the previous slide, they would all fit in an area the size of 5 square millimeters. About this big, little teeny tiny. So the point I'm trying to make is atoms are mind-bogglingly small. In spite of their small size, though, they are the key to connecting the microscopic and the macroscopic world. Things that we cannot see because they are too small, with things that we can see. So an atom is the smallest identifiable unit of an element. There are about 91 naturally occurring elements and over 20 synthetic elements. Those are elements that are not found in nature. And scientists are continually working on finding more, well, not finding, actually creating. And so on the periodic table up here, you'll notice this bottom row has all the letters there are white. Those are all the man-made elements. And this periodic table is a little bit out of date because we have some here with 3-letter names, and the first 2 letters are U, UUT, and UUS. Those are abbreviations for some weird numbering system. Those hadn't been named yet. But now, just a couple years ago, they were named. We just have not replaced all of our periodic tables yet.